Okay, I'm back, and now we are going to review our last lesson for the Unit 2 lecture exam. And so this is going to be lesson number 19 on light waves. So remember to read the lesson objectives. This is going to correspond to chapter 29 out of your textbook, and it's going to be sections 2 through 5. All right, first, a review of interference. So what does interference mean? There were two kinds of interference, constructive and destructive. So any time that you got one wave that is going like this and another wave is being superimposed on top of that wave, but let's say that whenever this one's going up, then this one is going down, and then whenever this one's going down, then this one's going up, and like this. So they have to have identical amplitudes, and they have to have identical frequencies and wavelengths. But they're out of phase. Another way of saying this is that they are 180 degrees out of phase. And so when you add the two together, you get nothing. Okay, so this is total destructive interference. Okay, but you could have a situation, let's put it over here, where you got the same wave, so it's going up and down, so it's still the same frequency, it's still the same wavelength, but this time we're going to superimpose it on top of a wave that is also going up when this one goes up, and then it goes down when this one goes down, and then it goes up when this one goes up. So this time, when you add them together, you get an extra tall wave. So it's going to be something like this. So that's going to be constructive interference. Now, if it is light, what does constructive interference look like to your eyes? Extra bright. What does destructive interference look like to your eyes? It's going to be nothing. It would be black. You wouldn't see anything. If it was sound and it was constructive, what would you hear? Extra loud. And then if it was destructive, what would your ear hear? Nothing. So that's the consequence of constructive and destructive interference. Okay, now there are certain circumstances under which constructive and destructive interference occur. So case number one is you've got two waves that are the same wavelength and have the same amplitude, and what we're going to do is change the distance that the light travels. So one light ray might start over here and travel to the wall, but another light ray might start here and travel to the wall. Well, it's possible, depending on where the light starts from, that it could end up being either constructive or destructive. So distance determines whether it's constructive or destructive. Okay, another one is it depends on the wavelength of the light. So if you've got one color of light and another color of light, and they're traveling the same distance, they could end up hitting the wall constructively. But if you have two different colors of light, they might hit the wall destructively, and then you wouldn't see those colors. They would go away. And then the third thing is it depends on the angle. So the light could be coming in at this angle and then bounce off something and go into your eye, but the light could be coming in at a different angle, and at a different angle it could end up being constructive or destructive. And so that's what's illustrated in this picture. So the reason why this is important is we're going to apply this idea of it depending on the distance, depending on the wavelength, depending on the angle, in order to explain different kinds of interference. And so the first kind of interference that I want you to be familiar with is going to be this one. So, talk amongst yourselves. You know, in the future, there will be a button that you just press, and then all of this goes away, and then you can start it up again. But it hasn't happened yet. So I'm old school. I'm wiping it away. All right, where were we? Okay, so this one here is you've got a series of light waves that are coming in this direction. And then what it's going to do is it's going to hit a slit. So as this wave travels through the slit, it's going to make ripples that are going to do this. Now later we're going to find out why are those ripples, why are they circles? Just don't worry about that. And then this one is also going to make circles when it goes through it. All right, and then what we want to know is at certain places over here, is it going to be constructive or destructive? So if it's on a line, it has to be a crest. If it is in between a line, here's a line and here's a line, so in between the lines, it's a trough. So can you see that, like right here, you have a crest of this line and a crest of this line meeting. So what did we call that, a crest and a crest? That's constructive interference. So that means the light is going to be extra bright right here. And then there's going to be some places where it's going to be extra dark. And then that is going to be destructive interference. Okay, another, and so there is a formula for this. You're not responsible for the formula. But this formula allows you to actually calculate where is it going to be bright and where is it going to be dark. And look at the formula, and do you notice it depends on the wavelength, and then it's depending on distance, so it's the distance between the two slits, and then it's depending on the angle. Well, those were the three things off of this chart. So don't worry about the formula. Okay, our next one was called Newton's rings. So be able to draw a picture of Newton's rings. So you're going to have a piece of glass, and then resting on top of the piece of glass is a curved piece of glass, like this. And then the whole thing, this is the sideways view. So the top-down view is the piece of glass is actually circular, like that, and then it's resting on top of another piece of glass. So this is the top-down view, and then this is the sideways view. So light coming down can do one of two things. The light can pass all the way to this piece of glass and then be reflected back up into your eye. Or this light could go into this piece of glass and bounce off of that surface right there. So when it bounces off that surface, it could go into your eye, and it could go into your eye either constructively or destructively, depending on this distance right here. So the distance between the curved piece of glass and the flat piece of glass, depending on that distance, it could be constructive or destructive. And so what you end up with is a series of circles. So where you see the circle, that's constructive. Where you don't see a circle, the circle appears black, that's going to be destructive interference. So notice that it's going to depend on the color of the light, the wavelength, and it's also going to depend on a distance, the distance between the two pieces of glass. It doesn't depend on the angle. because it's straight down and then it goes straight back up into your eye. The reason why it looks like it's at an angle in that picture is otherwise you wouldn't be able to see the lines if I superimposed them on top of each other. Then you've got gasoline floating on top of water, and you have soap bubbles. It's the same thing. So both the gasoline on the water and the soap bubbles are really the same thing. So that you're going to have light, it's going to come in and bounce off the surface of the gasoline into your eye, but some of the light will go through the gasoline and bounce off the water underneath it and then go into your eye. The same thing with the soap bubble. Some of the light bounces off the outer edge of the soap bubble, and some of it bounces off the inner edge of the soap bubble and goes into your eye. And it could either go into your eye constructively or destructively, depending on the wavelength of the light, also depending on the thickness of the gasoline or the thickness of the soap bubble. And then it does depend on the angle, so that if the light's coming in like this, you might be constructive, but if the light's coming in like this, it could be destructive. And so that's why you see different colors. Okay, now for the exam, it's going to be one of those four. Okay, so it's either going to be the gasoline on the water, the soap bubbles, or Newton's rings, or the double slit. So it's going to be one of those four. All right, so that was the concept of interference. So part 2 of this lesson is on diffraction. So we've already talked about reflection, the bending of a wave when it bounces off of something. So when a wave bounces off of it, that's reflection. We've also talked about when a wave goes through a material. So let's have it go this way. That's going to be called refraction, the bending of a wave when it goes through a material. This time it's going to be the bending of a wave when it goes around an obstacle. And so this is going to be called diffraction when this occurs. And notice that when a wave goes through a single slit, it opens up into these circular things. And we can actually predict where or how much it's going to do this. So if we, this is a simulator that showed how it works, but here is the formula that allows us to calculate where you're going to have constructive and where you're going to have destructive interference. Notice that that formula looks remarkably like that formula. So you notice that it depends on the wavelength of the light. It depends this time on the opening. So A is the opening that the light goes through, and then it also depends on the angle. Now what I would like for you to remember is, when will something start to open up whenever it goes through an opening? And it has to do with the wavelength of the wave. So if the wavelength of the wave is smaller than the opening, the wave basically doesn't feel the edges. And so it tends to go in a straight line through the opening. If, on the other hand, if the wavelength of the wave is equal to or greater than the size of the opening, then it starts to open up when it goes through. And the amount that it opens up depends on the wavelength. So it starts out with hardly any opening up because the wavelength is too small, and it doesn't feel the opening that it's going through. But as the wavelength is increased, you will notice that it spreads out more and more when it goes through that opening. Okay, and then our final thing was on polarization. So we did interference, we did diffraction, and now polarization. So how does polarization work? So the top picture shows light, and we said that light had an electric field, and then there was a magnetic field that was always perpendicular to it, and it was going like this. The light that comes out of the sun is unpolarized. That means some of the light is like this, that's the electric field, but some of the light's like this. And some of the electric field is like this, and some of the electric field's like this. So that the orientation of the electric field can be basically in any direction that it wants. That's called unpolarized light. Now, the magnetic field is still perpendicular to it. So if the electric field's like this, the magnetic field's like that. If it's like this, it's like this, like this, it's like this. But we don't care about the magnetic field. So let's just concentrate on the electric field and what it does. There are certain kinds of materials called polarizers that can stop the electric field. And a polarizer acts like a picket fence. So a picket fence is going to have slits in it. And similarly, a polarizer has slits in it. And so if the electric field is up and down like this, it has no problems getting through the picket fence. But if the electric field is like this, so it's trying to go side to side, and the picket fence is up and down, it blocks it. So that light doesn't get through the polarizer. So what's that got to do with polarizing sunglasses? So the idea of light from the sun is unpolarized. So that's this picture here where I've got the electric field going up and down. I've got the electric field going sideways. I've got the electric field at an angle. So that's the light that is coming towards you from the sun, unpolarized light. But when it hits a surface and bounces off of it, it becomes polarized. And so that's why I've got a line like this. It's been polarized sideways by the surface that it bounced off of. Now all you've got to do is be wearing glasses that are polarized like this, and you see that it's going to block this, and this is going to be the glare that's coming off of something. So that's the way polarizing sunglasses work, is they block certain orientations of polarized light. That's it. All right, so there is our review for the Unit 1 exam. And so after you take your exam, it will be time to start did I say Unit 1? I meant Unit 2. It'll be time to start Unit 3, and Unit 3 is going to be on motion and on forces. So I will either see you for the exam or I will see you for our next lesson. Bye.